power electronics, we work with a lot of periodic waveforms. A common one you'll see is a sine wave. I think people are familiar with that. We also may work with other types such as square, triangle, or sawtooth. When working with these kinds of waveforms, we want to look at some different values about them. And the two main things we'll want to look at are the average value and the RMS value. So here's an example. First, let's start with just a sine wave. If we look at this value, we see it's periodic. This is actually the ending point. This would be the end of the period. So for that period, we want to see what is the average value. Well, if we integrated here and here, we see the top and bottom are equal, and we see that the average value here would be 0. We also have this thing called the RMS, the root mean square value. And we'll see if we do the calculation, we're going to explain it in a second, but it's actually going to be a non-zero value. And for a perfect sine wave, we would see that the value is actually a over square root 2, if it's a is the amplitude here. So the average is, I think, more intuitive. You have a signal. We're going to work with current. So we're going to look at I over t. So we take I of t. We want to find the average value. So we integrate over the period that we know from 0 to t. And then we divide. So integrate the whole value from 0 to t. And then divide by the period to get the average value. And in this class, we're going to use square brackets to denote the average value. Then we have this root mean square, and here we're doing something a little bit different. So think about this backwards. We're taking our I, this is actually I of t, we're squaring that value, and then we're going to take the squared, integrate over the period, divide it by the period, so this is the same, the mean is the same as the average here. So we're taking the mean of the squared value, and then we're going to take the whole square root of that expression. So root, mean, and then square. So here, this is our sinusoidal waveform. We found the average is 0, right? But if we actually took this, say this was current, and we connected it to a resistor, the power would not be 0, would not be average 0, because the resistor would generate power during the positive part here, and also during the negative part here. So the RMS value represents the equivalent current, we're going to stick with current, value if you had connected it to a resistor. Okay, so let's say we're calculating the power. I say there's a periodic current, and we're putting it over resistor R. So let's start, just look at here. So we have the current, putting it through a resistor. We know power is equivalent to I squared R, and this is instantaneous, so this is over the whole period. So we take this expression, this is power, and we say, okay, we're going to take the average value of the power. We want power. Okay, so then we go from 0 to t, the period, divided by 1 over t. Okay, and we want to say, if we look at that power, can we write I, this big I, meaning RMS value, can that be just one value? What would be the equivalent here? Okay, so if we go to the next step, we say, well, we have r's on both sides. This r is constant. We take it out. We can get rid of each r on each side. Okay, then we're left with this I squared on the left, and then the same equation here. So all we did was remove the r's, and then if we square root both sides, we get I, the RMS value, essentially equivalent to the square root of the mean or average of the squared instantaneous value. One question, is the RMS value always greater than or equal to the average value? If you look back at the equation, you can think about it. One is squared, one is not. So find the answer is yes, the RMS value is always greater than or equal to the average value. These are the definitions you want to remember. Average and RMS value for periodic waveforms. We'll be working a lot with sine, but there are also other ones that you can calculate these values for.